We're going to also learn about the intermediate value theorem, which I will often abbreviate as the IVT. And just a reminder that in mathematics, a theorem, you could kind of think of that informally as a rule, but the words theorem and postulate both describe rules that can be proven to be true. So the intermediate value theorem has everything to do with continuity. So the IVT will tell us this. Let's start out just thinking about if we know that a function f is continuous on the closed interval 1 to 4. So remember, in interval notation, the hard brackets like that means values including 1 and 4. So we're continuous from 1 to 4. We also know that f of 1 is 5 and that f of 4 is 1. So on this graph, f of 1, if that's equal to 5, I'm going to put a point up there. F of 4 equals 1, I'm going to put a point there. The only two things we know is that our function is continuous from 1 to 4, and we know those two values. I guess that's three things that we know. So we know that if our function is continuous, that informally we should be able to trace it from one point to the other point without picking up our pencil. So who knows? Maybe it's linear. Like maybe that's what our function looks like. That could be the case. Or maybe it doesn't look like that. Maybe it's curvy. Like maybe it kind of looks like that. The fact of the matter is we have no idea what that function looks like. We only know two values, and we know the function f is continuous from 1 to 4. So we're asked this next question. Must there be some value of x, which is an element on the open interval from 1 to 4? So that's just a fancy way of saying, must there be some x value between but not including 1 and 4? So that f of x is 3. So must it be the case that if this function's continuous, somewhere between x equals 1 and x equals 4, those inputs, we get an output of 3? And the answer is yes, because no matter where we draw that, so like right now, the way I drew this last curve, we'd have an output of 3 there, and there, and there. So we could have 3 outputs of 3. If I go back to the first way I drew it, where it appeared linear, maybe we just have 1 output of 3. But you cannot go from y equals 5 to y equals 1 on the number line without passing the number 3, because 3 is between 1 and 5. And since this function is continuous, we must pass through 3. So that, in a nutshell, that's what the intermediate value theorem is telling us. So when we answer this question, well, the answer is yes, and here's what we know. We know that f is continuous, and we want to get in the habit of like writing this interval notation. So I could say on the closed interval 1 to 4. I also know that f of 1 is 5, and I know that f of 4 is 1. And I know that the number 3 is between those numbers. So 3 is between 5, or f of 1, and 1, or f of 4. So because of all of that, because of those 3 facts, the intermediate value theorem proves that there must be some input between 1 and 4 that yields an output of 3. So again, when I say output, that's like our y value. Input is our x value. So this is the answer to this question is yes, and it's by the intermediate value theorem that we know this. And you can abbreviate IVT. Everyone will know what that means. All right, so let's get to the definition. And again, anything in a box is going to be so important. So I might even have like 3 note cards right now about the 3 boxes I've seen in this first lesson. So I'm going to tell you right now, you need to memorize this. The way this is written is so important. This is a conditional statement. Most theorems are. and I'm going to refer to it as having a hypothesis and a conclusion. So when I say hypothesis, I mean everything that comes after the word if. That's the hypothesis in a conditional statement, the phrase that comes after the word if. The conclusion is the phrase that comes after the word then. And as I'm saying that, I know the word then is not literally written here, but if it were written there, it would go right there after the comma, and this is what we can conclude. So we can draw this conclusion based on this hypothesis being true. So if a function, in this case f, is continuous on the closed interval from a to b, oh, you know what? We do have the word then. Oh, that's rough. I did not read that very well just now. Okay, sorry. Here's our conclusion. Wow. I should go back and fix the video, but I'm not going to. If f is continuous on the closed interval a to b, that is the hypothesis of this theorem. That is the condition that must be met for the conclusion to be drawn, the hypothesis of the conditional statement. Then the word that is written there for every k, and remember, the way we're seeing this, k is going to be an output. So for every k between f of a and f of b, these are all outputs. So for every output, there exists a c on the open interval a to b. That's going to be an input, it's like an x value, such that f of c is equal to k. So I realize it looks really confusing when you read it like that, but if we go back to this graph, we said we know without a doubt that f of 1 is 5, f of 4 is 1. So for every number between 1 and 5, every output, every y value, every function value between 1 and 5, between 1 and 4, there has to be some value of x where the function takes on that value. So like the y value 2 has to exist. Who knows? Maybe it's like this on the linear function. Maybe it's here on that curve I drew. That's really what the IVT means. I know it's confusing at first. We call this an existence theorem. It guarantees the existence of the value c, but it doesn't tell us what c is, so we have to do a little more work for that. All right, let's look at this example. Let f be a continuous function. When we're not told on what interval f is continuous, we can assume f is continuous everywhere or everywhere across its domain. So let f be a continuous function with selected values given in the table below. And the first question is, must there be a c on the interval from 2 to 3 such that f of c is 3? So again, c is an input, 3 is an output. So from 2 to 3, I'm going to look from the x value 2 to the x value 3. And I notice my y values, my outputs, so in, out, my y values range from -1 to 4. 3 is between those numbers. So yes. So when we want to earn full credit on a free response question, which we always do, we have to include the following information. We have to confirm that f is continuous. We have to restate the hypothesis, and it's got to be true. And then we need to confirm that 3 is between f of 2, which is -1, and f of 3, which is 4. Therefore, the intermediate value theorem guarantees some c on the interval, again that means is an element of, but I'm going to say on the interval, from 2 to 3, such that f of c is equal to 3. All right, let's look at the next bullet point. Must there be a k on the interval 1 to 2 such that f of k is 5? So I'm going to erase this. I'm going to go look at 1 to 2. So from where x equals 1, my input, to x equals 2, my output, we have the outputs 3 and -1. So if I just think about this on a graph, when x is 1, my output is, let's say, here at 3. when x is 2, my output is down here, say at -1. And the question is, must there be a k value between 1 and 2 where our output is 5, which I'm imagining would be like up here, maybe 5? Well, no, not necessarily. I could go from y equals 3 to y equals -1 without ever passing the number 5, because 5's not between -1 and 3. So here's where we have to be careful. We can't say that no, there isn't a value, because it's possible. It could happen. But what we can say is that the intermediate value theorem, the IVT, does not guarantee k on the interval 2 to 3 such that f of k is 5. And why? Well, we have to give a reason, and that's because 5 is not between f of 1 and f of 2. So 5's not between f of 1 and f of 2. It's not between 3 and -1. So the IVT can't guarantee that value, but it is possible. All right, the last bullet point, h is f of x squared. Must h have a 0 on this interval? Well, remember, to use the intermediate value theorem, we would have to know that h is continuous. We were only given the fact that f is continuous. So if you go back to page 2, just below that box, there was some information here that we said on page 2 that if f is continuous and that g is continuous, that all of these things have to be true, like f plus g or f composed of g. So as I'm looking at this function h, it's a composition function. It's the function f composed of x squared. And let's think about what we know. We know that x squared is continuous. We learned that in algebra. So like x squared is continuous. We know that f of x, we were given that f is continuous. Therefore, h is continuous. So again, h is a function that is f composed of x squared. So we could use that property to confirm that h is continuous. And this is important because we cannot use the intermediate value theorem unless we prove that h is continuous. So we're now asked if h must have a 0, so must have an output of 0 on the input interval from 0 to the square root of 2. So we need to evaluate h of 0 and h of the square root of 2. Well, h of 0 is just f composed of 0 squared, which is f of 0. And we could see in our table that that is the number 10. H of the square root of 2 is f of the square root of 2 squared. Well, that's just f of 2, right? The square root of 2 squared. And that's going to be -1. So, must h have a 0? Well, yes, 0 is between -1 and 10. So we could say, like, yes, since 0 is between h of 0 and h of the square root of 2, we already wrote out what those are, the intermediate value theorem guarantees c on the interval from 0 to the square root of 2 such that h of c equals 0. All right, finally, this last example, we're given h of x. Does the IVT guarantee a c between 0 and 2 such that h of c is -1? If so, find it. And then beneath that, the same question with a different interval and a different output. So again, going back to this hypothesis, we could save ourselves so much time if we first check the continuity. So where is the only place h of x would not be continuous? The only possible candidate for a discontinuity? Again, this is not a piecewise defined function, so I'm just looking at this denominator. And if x minus 3 equals 0, and that happens when x is 3, we're going to have a discontinuity there. And in fact, we would have a vertical asymptote, because if you evaluate h of 3, you get 4 over 0, not 0 over 0. So I got to look out for that. But this interval from 0 to 2 does not include 3. So we could start by saying h is continuous on the closed interval from 0 to 2. And then we also need to evaluate h of 0 and h of 2. So h of 0 is, let's see, 0 plus 1 over 0 minus 3, negative 1/3. H of 2 is 2 plus 1 over 2 minus 3, which is negative 3. So, since negative 1 is between negative 1/3 and negative 3, our answer is yes. So, yes, IVT guarantees h of c equals negative 1 for some c that's an element from 0 to 2, because negative 1 is between negative 1/3 or h of 0 and negative 3. The College Board's so picky about intermediate value theorem responses. We've got to establish continuity. We've got to assert betweenness, and I'm sure we'll have that conversation a lot this year. Okay, then finally, it says, if so, find it. So now we're asked to find what that input is. So remember, IVT can't really help us with that. IVT just proves it exists. So if I want to know when h is negative 1, I need to set my function h equal to negative 1 and solve for x. So let's see, if I multiply both sides by x minus 3, I'm distributing that negative 1 to x minus 3. I get negative x plus 3 or 3 minus x. I could add x to both sides to get a 2x plus 3 equals 3. Oh, you know what? I copied this wrong. Sorry, that was supposed to be x plus 1. Oh, man. It's the second mistake I've made. All right, so sorry, we keep the x plus 1. We said if we add x to both sides, we'd have 2x plus 1 equals 3. Subtract 1, we get 2x equals 2. So x equals 1. So therefore, c equals 1. And maybe I should have used c's and not x's there. So yeah, there is a value of c where this happens. It's when c is equal to positive 1. H of 1 is negative 1. All right, finally, the last bullet point. Does the IVT guarantee a k on the interval 1 to 4 such that h of k is 0? If so, find it. Well, no. And why not? Coming back to this piece. We cannot use IVT on the interval of 1 to 4. So what I just might write here is, since h of x is not continuous on the closed interval 1 to 4, IVT may not be applied. We won't say that it proves that there's not a value. We don't know. We just cannot use IVT.